This question, we have a graph, so the first thing we want to do is do our analysis. And it turns out that our analysis of the graph using Euler-Zerga is essential for answering this question. So O, Y, X, R, G, A. Now the origin, we see, really is here, so it's in a normal spot. Our y-axis is L, the angular momentum, which is in its normal units. The x-axis is in time, in its normal units. So therefore, any questions about angular momentum or time will simply be read off the graph. Now the slope is delta L over delta T. So this is where we want to pull out our basic knowledge that we have, and we want to start with our four-way equivalence. We know that in the linear world, the impulse is defined as the average force times the time over interval over which it's applied. We know that the change in momentum is the mass times the change in velocity, and that the impulse brings about a change in momentum, and that change in momentum is equal in magnitude to the impulse, so we end up with our four-way equivalence. Now we can go to our rotational equivalent. We have our angular impulse. Now, instead of it being forces, we have torque. So the average torque times the change in time will equal the change in angular momentum is equal to the moment of inertia times the change in angular velocity. So the slope gives us the rate of change in angular momentum. So we have delta L and the rate of change delta T. Pulling those two out, we can rearrange them, and we see that the torque equals delta L over delta T. So delta L over delta T is the torque. Now, of course, if we think about this that's the rotational world, if we think about it in the linear world, the definition of force is the rate of change of momentum. So rate of change of momentum is the force. The rate of change of angular momentum is the rotational force, or the torque. So we get that comparison there. Now looking at the area, we have L times delta T. Now if we were to do that for momentum, pull these out, multiplying delta T, even if we did this, F delta T equals delta P, multiplying both sides by delta T is F delta T squared is delta P delta T. It is something, but it's not a basic concept that we have or would use on a regular basis. So this tells us nothing of use. So now, going to the question, now we can get to the question. Let's label our curves here. We have an object y, given like so, and we have an object x, like so. So now they experience external torques that vary. And the torque, we said, is the slope. So what that means is, well, if the torque is the slope varies for y, and the slope varies for x. Object x has a moment of inertia of I-O, and y has a moment of inertia of 2I-O. All right. The average value of the magnitude of the external torque. Average value. So the average slope on x from time 0 to time 5 is tx. From 0 to 5 or tx. The average torque. Well, the average slope would be this. That green line. The average torque on x. Similarly, the average value for y is the torque on y. So that would be the average force on y. So these are shown on the graph. Which of the following expression correctly relates y to x? Well, this is the torque on y, which has a slope, and we could calculate it. It actually has a slope of 20 over 5, which is 4. And for x is 10 over 5, which is 2. So y is not 4 times x. Y is 2 times x. X is not 2 times y, and x is not 4 times y. So the torque on y is 2 times x. So this question requires us to really know and understand the relationships and similarities between linear and rotational momentum torques and be able to read and interpret those off the graph.